Good morning, everyone. Welcome to today's Daniel Chase lecture. Today we have very glad to have Professor Matthias Scheffler to give this Daniel Chase lecture. Matthias now currently is Fritz Haber Institute of Max Planck Society, and he's particularly known for his contribution to the development of electronic structure theory, thermodynamics, and statistical mechanics for material sciences. And Matthias got numerous prizes, and in 2010 he got a Rudolf Jacke Prize of Germany Vacuum Society, and also many lists. Okay, so I will not say too much about his great achievement. A long list. Okay, but we just had an international conference for Matthias and celebrated his 70th birthday. Okay, and I think I'm very impressed by Matthias. Is he had like more than 100 students currently working on in the field of physics, and I heard that he had 24 professors, in China, in this field. So it's a big community. I think he made not a big contribution to the physics entire world, but particularly he made like very important contribution for China. Okay, so let's welcome Daniel Cui, Professor Matthias to give this Daniel Cui's lecture. Before the lecture, we will present the Daniel Cui lecture certificate to Professor Matthias. Please welcome Professor Matthias to come to the front. Okay. Yeah. Let's do this.
Okay, thank you.
Okay.
Thank you.
Thanks.
Thank you very much.
Okay. So let's welcome Professor Matthias to give his lecture.
Thank you. Yeah, thank you for the nice introduction. Thank you for the certificate. I mean, usually one gets these certificates after the lecture, right? Just because then you have seen if it really is worth it. No, I have it already. So thank you very much. No, it's really a great pleasure to be here. Again, I would say, as you have said, I have actually very many friends in China, but also in fact at the IOP, and these quite good relationships with the IOP started, or actually got intensified in the year 2000, when Enge Wang and Zhenyu Zhang created this International Center of Quantum Structures, ICQS, and I was on the advisory board. And since then, actually, I was really visiting pretty often, and I think what Enge and when we really succeeded in also making this place more international visible, which before 2000 there was still some possible, but now I think also seeing the workshop which Xingu has organized, I mean the quality and the visibility of the science in China is really very impressive. So thanks for having me here, okay, so I will talk about finding rules and genes for materials, properties, and functions by artificial intelligence. Now, there are two important words in this title that may not be clear to everyone, and these important words are rules and genes. They reflect important concepts, which I hope will become clear during my talk. So let me explain, and you see here the title again. what I really try to convey in this talk. I will briefly discuss developments of research paradigms in material science, the current direction in material science, and the new paradigm, which is the basic concept behind my talk, is associated really with using artificial intelligence methods for analyzing scientific data. And the key issue here concerns the identification of correlations, which is quite different to the classical approach in science, which is aiming at causation. I will discuss later in more detail and with specific examples what I really mean by that. In fact, I will describe certain artificial intelligence methods which bring some of the causation back. And we feel that bringing some of the causation back is indeed very important. And this brings me to the concept of materials genes and rules. Materials genes are basic materials features or basic materials characteristics that play a similar role as genes in biology. So that features could be local structures, or there could be certain aspects of the wave functions of the atoms which build the solid, or other properties of basic properties of a solid. And the property of interest, which we like to describe or associate with these genes, these properties of interest could be, for example, if you think about catalysis, the catalytic performance, or it could be, if you think about solar cells, the band gap of semiconductors, and so on. However, the scientific explicit relationship between genes and this property, they are not known explicitly. And that is basically, again, like genes in biology. You know that these and these and these genes are responsible for a certain type of illness with a certain probability, but you don't know really the relationship. And that is also somewhat true here. And it enables us to describe things which are very intricate, very complicated, and things which cannot be described in terms of a meaningful equation. Again, we are measuring correlations and not necessarily the 100% causation. And therefore, in fact, we say what we get out from these genes and from the relationships is not really derived explicitly from scientific laws, and it cannot be completely explained in terms of explicit laws, and therefore we are not calling them laws, but we're calling these correlations, that these correlations are described by rules. So that is the reason of these two words which we have chosen. And this is the essence of the fourth research paradigm of material science. This idea represents a new way of thinking where we are now largely ignoring theoretical physics. We are largely ignoring physics laws and physics education, but we are looking for correlations instead. Now, let me actually, what I just said, make it a little bit more positive, because ignoring all that doesn't really sound very helpful. So in other words, actually, it means, in a more positive phrasing, we acknowledge that there is a higher complexity in the world than that which can be described by classical mathematics and by partial differential equations as given by the known scientific laws. As noted here, this is the essence of the fourth research paradigm of material science. And let me briefly remind you about the other paradigms. The first paradigm was really experimental physics, or you can also say empirical physics. The second paradigm is theory. That means the idea, the concept, and what we have seen that observation can be generalized in terms of partial differential equations, like the Newton's law, like Maxwell's equations, like the Schrödinger equation. And the third paradigm then was, as some of these equations are very nice, but they cannot be solved, to solve this equation by high-performance computers and very complex computer program. and which sometimes is also called by doing computational or computer experiments to really also get some insight. And then you analyze the data in a very similar way as experimental colleagues are analyzing them. Now, that all implies that when we do artificial intelligence, and to some extent that is often forgotten, we are doing, in fact, a statistical type of learning. And that means the prediction by artificial intelligence, as it measures correlations, are not just really a number. Typically, people give just a number. But in fact, there is a probability related to this number. And there is also a certain width of uncertainties. And so there's a statistics and probabilities, and that is one thing which I really think, and I will emphasize this later in my talk, one needs to really keep in mind when doing artificial intelligence. So if one likes to employ artificial intelligence, or if one likes what is also called do data-centric science, the obvious point is that one needs data. Right? Without data, you cannot do data-centric science. And therefore, we started about 10 years ago to build an infrastructure that enables a fair data sharing. And I've talked very often about this here and at other places up to probably 2 years ago. Since 10 years, I will not really discuss that really very much further. I just like to add or mention one historic remark. A historic remark which still shows a little bit of the problem which we are facing today. The critical importance of data collection and sharing has been well recognized since the very early times of science. And here's just one example, and that is the tense relationship between Tycho Brahe and Johannes Kepler. The former, that means Brahe, had comprehensively and accurately measured the motion of astronomic objects, Mars, Venus, and so on. And he, Tycho Brahe, had the best data of the time. You see actually here when he lived. But he guarded these data very carefully. He didn't want to share. He wanted to do the analysis by himself. Kepler was probably the best mathematician of that time. And he was very interested in Tycho Brahe's data. But he didn't get them. Only later in his life, and when Brahe turned actually 54, Brahe invited Johannes Kepler to become his assistant. Then Brahe's untimely death, about 1 year after Kepler had arrived, this death was a big chance for Kepler to get the data, because now he had access to the data. Now, there was an accusation that Kepler may have killed Brahe to get the data. Now, you don't want that this happens to you, so better share, I think. But actually, this accusation could not be supported on court. However, the relatives of Brahe argued, and there they were somewhat more successful, they argued that Kepler had stolen the data. Whatsoever. After Brahe's death, based on his data, Kepler developed what is now known as his laws of planetary motion, the Kepler laws. And despite this tense relationship, they are typically, and also here on this thing in Prague, honored together. Brahe for the measurements and Kepler for the interpretation. Each of them alone would not have achieved what they have achieved together, although this together has to be in quotes, because I just told you how this really was. Now, the Kepler laws have been very critical also for the later developments, and in particular really for Isaac Newton for developing the theory of gravitation. Now, this concept of converting information about nature into laws of nature, that is into analytic equations, is really related to these people, which you see here. And in addition, maybe Galileo Galilei and Gottfried Wilhelm Leibniz. And this describing nature in terms of equations is what I said before is called the second paradigm of natural and material science. Now, the Brahe-Kepler example concerns astrophysics, so let me actually now focus on material science, but we still have the same problem of sharing data and really combining people who really should work together and sometimes cannot really do this so easily. So why is material science, most of you are really from this field, important, so I don't really have to say very much. Why it's important, the prosperity and the lifestyle of our society are very much governed by achievements in material science, because new products and new sectors such as energy or environment or health, mobility or information technology rely largely on improved or even newly developed created materials. Examples are solid state lighting, solar cells, touch screens, batteries, also implants in medicine like teeth and hips, and drug delivery are really all affected significantly by developments of material science. Unfortunately, actually military as well, but we always try to ignore that if you're really a basic scientist. But today, big data and artificial intelligence revolutionize many areas of our life, and material science obviously is no exception. And there are in our field, there is really the need to develop also new artificial intelligence methods. The methods which are useful in say, social media or analysis of social effects, these are not necessarily really helpful for our field, because the structure and the amount of data that we have is very, very different. And so the chance which we have in doing data-driven science, but in fact also the daunting challenge, is listed here. So in principle, the number of possible materials is practically infinite. Now that sounds good, because it means that you have, okay, thank you very much. This sounds good because it really tells, having so many possibilities, there are very likely materials out there which we don't know yet, but they may actually be better for a certain function than the materials which we know. On the other hand, if there are so many, it will be also very difficult to find the right ones. And so what people so far are doing, and also really in history have done, is what is called high throughput screening, really doing a lot of measurements or a lot of calculations, let's say thousands or 10,000 of measurements or calculations. But even 10,000 is nothing compared to infinity. So it's very likely that you will miss what is really important. And the problem also is that we are not just looking, or we are not really interested in all the materials. We are interested, if you talk about catalysis, about a catalyst which is very good for a certain chemical reaction. And very good for a certain chemical reaction is really an exceptional situation in this infinite number of materials. And so this is why the situation is really characterized by this haystack. We are looking not for the general behavior in material science, we are looking for the statistically exceptional. And the way how we see this situation is that we say we should look at what we call maps of materials properties and functions using artificial intelligence methods and concepts. So maps means we need to find descriptors, so an x and a y-axis, and the x and the y-axis we call descriptors because they describe the material. They describe the materials in terms of the genes, which we have said, so we don't know actually what the descriptors are, but we are confident there are descriptors And if you have found the right descriptor, the right x and y axis, then in this infinite number of possibilities, there are smaller regions where you could find systems which are, say, maybe good thermal insulators, or systems which are good for heterogeneous catalysis or for something else. And then you zoom in only in these areas and try even there to make these areas smaller because you're looking only in for a certain subgroup of these. So creating maps of materials is the concept which we are following since, I would say, a little bit more than 10 years. And finding descriptors is really the issue. And this is what I like to discuss first. And I will then, because I always think it's nice and good to explain things with examples, because then you see a little bit more actually what you can do with this. So I will really explain these things in terms of examples from heterogeneous catalysis and from thermal insulators. So the challenge in science, in material science in particular, is to uncover regions in the data, which are infinite number of materials, uncover regions that are statistically exceptional, where you have a good chance to find the needle in this big haystack. So this is here a tutorial picture which shows, I think, about 1,000 data points, again as a function of, of descriptor D1, the x-axis, and descriptor D2. I use this really as a tutorial picture at the moment. And if you look more carefully, there are materials descriptors D1 and D2, the x and the y-axis, and there's a property y, and the property y can have two values, a and b, or in fact, if you look, it can be squares or circles. So it's a very simple example. And we asked ourselves, how can we find these descriptors D1 and D2, and how can we find exceptional regions? Now, first a word about how things are done in, let's say, general machine learning. Machine learning is using what is called a global model. That means they're trying to do one description for the whole population. So population means all data point which could be there. And here, from the infinite number, we know 1,000. So having one model for the whole population, this is what machine learning typically is trying to do. So minimize the overall prediction error by also using regularization, which in simple words means by make sure that the fitting or the description is somewhat in a reasonably smooth function. This also implies, because you have a regularization or you have some type of smoothing, it implies that one disregards local details on purpose. But if you look for the statistically exceptional, we may actually be just interested in these local details. And so what we are doing, and this is the first example we are using, is what is called subgroup discovery. And I have two people here, Yilis Vreken and Mario Bolai, because these two people really taught us what one should do to do it. And I describe this now in a little bit more detail. So what we are doing in subgroup discovery means we go through all the data points and we asked if there are Boolean conditions. Are there descriptors or are there quantities where you can say if this quantity is bigger than, say, descriptor D1 or is an element is in a certain range of descriptor D1, which actually helps or goes together with the exceptional property. And we combine several Boolean conditions, as many as necessary, into what is called a conjunction. So sigma describes a subgroup which is identified by several Boolean conditions. And what these Boolean conditions are is done in a Monte Carlo way by going through all the data. And of course, at the end, when we find the best Boolean conditions, that also tells us, in fact, what the descriptors are, because they relate to the Boolean conditions. And so looking at this example here, you see two subgroups immediately, which you would have also recognized by eye. Sigma A on the bottom and sigma, actually on the top, and sigma B on the bottom. So sigma A, this subgroup is defined by D1, the x-axis being between 0.25 and 0.75, and D2 should be bigger than 0.9, and sigma B is defined in a different way. And these are, in this case, really pure subgroup. 100% circles on the top and 100% squares. No, actually other way around. 100% squares on top and 100% circles at the bottom. Now, again, I mean, these subgroups would be only visible if you use these descriptors D1 and D2. If you would use other descriptors, you would not see them. So descriptors and identifying subgroups is done really together in the subgroup discovery. But we also don't really ask for 100% pure subgroups. Here is another subgroup, which is here in the middle, which is dominated by squares. So it's not really 100% squares, but it's really dominated by squares. So we go through all the data, we look for certain conditions, and we hopefully find then that from everything which we offer and test, we find a certain good choice. Now let me now explain that with an example, that you really see what you can do with this and what maybe also you see more clearly what I really mean. And this is the example from catalysis, propylene oxidation at a multi-component catalyst. This was work together done with the company BASF and another smaller company, which actually meanwhile has been bought by BASF, which was HTE, which is high throughput experiments. But the work has been done really by Lukas Fopper from our group, who is a theoretician. So propylene oxidation is something which you are interested in industry. It means that you have really propylene, you combine it with oxygen, and you want, in fact, you want one of the two top chemicals, acrylane or acrylic acid, so the purple or the green one. Now, but if you really combine propylene and oxygen, the best reactions with the most energy gain would be burning it completely, so complete combustion, namely forming CO2 and carbon monoxide. So how can you really find a catalyst which is not doing the combustion, but creates as much of these so-called oxygenates, the purple and the green one? And we started with data, really experimental data from the company. These catalysts were made from tungsten, from ruthenium and phosphorus in a different type of proportion. Now, there was also oxygen in these materials, but there was no way to really quantify the amount of oxygen, and it also seemed that the oxygen amount changed during the reaction, so it was at the end probably even a result of the reaction, but we didn't know that. So that's why I'm saying these are three-component catalysts, tungsten, ruthenium, and phosphorus in different proportions. And these catalysts were nanoparticles, or actually bigger particles also, put on a support material, namely silicon dioxide. Here you see the experimental data. So every point in this triangle is a different composition of phosphorus, of ruthenium, and tungsten. So phosphorus on this axis here goes from 0 concentration to 100%. Here goes ruthenium from 0 to 100%, and here goes tungsten from 0 to 100%. So every point, even the one which are not measured, so the points which you see are the measured points, but any other point is also possible, right? So again, every other point is the full population, and from the full population we have 120 catalysts measured. You also see here the yield, so how much oxygenates are created at 300 centigrade. Blue means basically everything is burned and nothing good is created, and yellow means 25% of the yield is in fact the wanted product. So we have 120 catalysts, and most exhibit a low performance. And you see, if you just look actually about the data which we have, Counts means the number of data which we have. So we have 1,220 data points at the end. So that means 120 different catalysts, but then different temperatures between 200 and 400 centigrade. Most of the data relate to catalysts which are not important, which are actually bad. And very few data have really a yield of oxygenates bigger than 20%. This is what is called a very unbalanced distribution of data. And having such an unbalanced distribution of data is also what gives machine learning often a very big trouble, because as I said before, you describe everything in machine learning, and then if most of the things are not really relevant, the error is optimized also at the non-relevant situation. So machine learning, and subgroup discovery is really concentrating on subgroups. So we are not and that means we do not look for individual data points of high performance. So we're not just cutting off some data, but we try to find rules or these Boolean conditions that identify a coherent subset of data, a group of materials that is defined by a concise description or by rules, as we said before. Only then we feel we also have something which goes with a similar mechanism, and then we can also generalize this to points which we don't have. If you just cut off the thing, you cannot really generalize this to other situations. So the subgroup that we finally identify are these black bars here. And from these 1,220 data points, the subgroup actually only has 15 data points. And it's not really exactly, it's not really following the orange line, so it's different, but it has a coherent description of a group which apparently follows a similar type of schema. So how are we doing this now in practice? The first thing is we have to offer quantities of features or physical chemical features, which we offer that the subgroup can test if these features are meaningful. You should offer as much as possible not to miss the relevant one. At the end, subgroup discovery will only use a few of these, but I think this is what the discovery process should really do. And so what we are using is obviously the temperature, if you want an external parameter, the environment. Then we use the content of phosphorus in the catalyst. That was a little bit the request from the industry, that they said, we had the idea that phosphorus could play a role, and we would like really to offer this as an external parameter, as a physical chemical feature. But then we use various theoretical numbers. We use theoretical free atom properties, which are calculated by density function theory in the PBE-SOL approximation. And that is, for example, electron affinity, or the ionization potential, or some properties of the p and the d electrons. But these are atomic features. They have, at this point, nothing to do with the solid. So we have to convert these atomic features into something which relates to the catalyst. And so we take atomic features, but then do the average according to the percentage, the materials in the catalyst. So these atomic features are converted into system-specific features by taking the composition weighted average. So sigma, phi I is really the calculated, let's say, ionization energy. Xi is the percentage of the material which is in the catalyst. So we multiply this and we sum over all the materials in the catalyst. In the data which we have, there are 3. So M is 3, ruthenium, tungsten, and phosphorus. And that gives us this concentration weighted average. And this is now, of course, relates to the catalyst material. But you also see that this can be generalized. I mean, we have this for 120 catalysts, but you can, of course, easily also say everything else can be described by another phi square, which corresponds to a different type of composition. And in fact, you can also easily generalize it even further. So these theoretical parameters can be evaluated for the not yet synthesized materials, and that can be 3-component catalyst, but you see that you can also really create a phi bar for a 4 or 5-component catalyst. So you have a possibility really to generalize your results. And here is what subgroup discovery finds. From all these offered features, subgroup discovery decides only 3 are really relevant. So we offer, I think, 17 features. We look if there are relationships which identify coherent groups, but then we see only 3 are really relevant, and these are the temperature, the phosphorus molar content, and the composition weighted electronegativity. And you see in orange the conditions. The temperature should be between 280 and 300 centigrade. The phosphorus content should be bigger than 55%, so pretty high to some extent, I would say. And the electronegativity should be in this range, which is also noted here. So you see here again this triangle. Every point in the triangle corresponds to a catalyst, and the dots are the measured catalysts, but now the color code is different. So now the color code just really corresponds to the electronegativity. And from the conditions which we had above, the phosphorus content should be bigger than 55%. That is the green line here. And the electronegativity changes from low. This is the line, the 3.9 eV line. This is the 4 eV line. So the good catalysts are predicted to be in this region. So you can create a composition, whatever composition you like, and then you see, is it in this upper region or is it somewhere else? And depending where it is, the conclusion would be this is most likely a good catalyst or a not so good catalyst. And we have done this for 3-component catalysts and tested that for additional ones and predicted several ones which then have been synthesized. But we've also used the same conditions for 4 and 5-component catalysts, much more complicated one. And we found when you used to go to 4 and 5-component catalysts, you find catalysts which have an even higher efficiency. And here is one which then also has been analyzed. Tungsten with only 5%, ruthenium with 5%, tellurium with 25%, thallium with 0.5%, and phosphorus with 60%. So this is just subgroup discovery tells us in this picture of clouds where you should really look in the cloud to find even a better performance catalyst. Let me come to a second example, which is very different, and that is in fact thermal insulators, where we are developing what we call an artificial intelligence guided workflow for experiment or actually for theory to find better and better thermal insulators. This is work done mostly by Tom Purcell in our group. Now, thermal insulators are really a special type of materials which are characterized by strong anharmonicity. Anharmonicity is really crucial because, I mean, if you have a system which is 100% harmonic, thermal conductivity would be very good and actually would be infinite. So to have a finite anharmonicity, a finite heat transport, thermal transport, you need anharmonicity. And if you want something which is even a thermal insulator, you need a very strong anharmonic material. And, and what we found is that for thermal insulators, you really have total energy. So this is the total energy of the atoms in the solid. So you have a total energy behavior like the one which you see here. Typically, it is assumed that the atoms are all sitting at a minimum of the potential energy surface. And they are just vibrating in this minimum. And what we find is that if you really have a strong anharmonicity, you are not only see that this minimum is not really in a part of a parabola. The parabola is strongly distorted, but it's not only just distorted, there are many other minima as well. And these other minima are defects. Defects which very often resemble another phase of the same material. So that's why we sometimes also call them precursors of a phase transition or phase transition embryos. And these happen already very far from the phase transition. You see actually that these defects are created, but only really on a very local scale. And so this is what we see actually when we talk about strongly anharmonic situations. And here you see how important that is. And let me actually say that also. That also means, of course, you're not just vibrating here, but you're also jumping to this other minimum. And that, in fact, means you're not just really having vibrations in a phonon sense, but something very different. So if you calculate or measure, in fact, by both the thermal conductivity, this is an example of copper iodide. This is the experimental data. So a somewhat good thermal insulator. If you do the standard type of theory, which is phonon-based perturbation theory, as done by these authors and by, I would say, nearly everyone else, you get this here. If you just really accept that you should not really start with phonons and perturbation theory, but you really do it as exact as possible without any approximation on anomalies, you would solve the ab initio Green-Kubo formula, which we have done in the last years, and then you're at least getting close to the experiments, whereas really in the phonon picture, you are pretty far from the experiment. Anyhow, what this really means, what this really means is you should not really, if it's strongly anharmonic, use a phonon picture. So I say throw out the phonons and only consider vibrations. Now, of course, if you consider vibrations, that includes the phonons. You're not really ignoring them, but you're just ignoring the mathematics behind the phonons. You don't assume that things are described in terms of a distorted parabola. And the way to do this is, as nature is doing it, just let the atoms move and vibrate as the atoms want it. And for theory, it means use ab initio molecular dynamics to explore the full anharmonic potential energy surface. The interesting thing is that a measure of anharmonicity did also not really exist so far. So how can you really say this system is anharmonic and another system is harmonic? And here a PhD student, Florian Knoop, did really very nice work to quantify anharmonicity, and we introduced this parameter which we call sigma A. And here you see what we really see, and this also tells you a little bit again about the physics of anharmonicity. You calculate in this molecular dynamics movement the forces on each atom. I mean, atoms move because there is a force, and they move back also because there is a force. So you calculate the force on each of the atoms of the solid. You then use what we call the anharmonic part of the force. And that is simply defined by using the calculated force, and you subtract from that the harmonic contribution. So you just assume there's also in your head a parabola, and this parabola has a derivative and has a harmonic contribution. And this harmonic contribution you take out from the true 100% fully calculated force. And that this difference we call the anharmonic part of the force. And sigma A is then the ratio of the anharmonic part of the force squared divided by the harmonic part of the force. The sum goes over all atoms, so the capital I is all atoms, and alpha is just the X, Y, and Z components. So in your molecular dynamics, you just really also evaluate this quantity, which is very easy to do. And if you look at it, you see in the molecular dynamics that this looks like the following. So what you see here are 5 different calculations. So you usually calculate an ensemble of different material, of different situations for the same material. So these are 5 representations of the ensemble of, in this case, is potassium, calcium, fluoride. And you see here in the first case of the ensemble, this goes, so the x-axis is the time, and the y-axis is really the sigma A parameter. So in the first thing, you don't see anything happening. And you see the atoms vibrate a little bit, but nothing is really happening. But on another representative of the ensemble, you see it's as before, but then suddenly it jumps to another situation, it goes back, and then it jumps to another situation and continues and stays here. So these are the defects, right? I mean, you really move from one geometry to another geometry, and you see that you can stay there for really pretty long. And then, of course, the average sigma A will be affected by all the jumps. And you see these jumps also in several other ones. But you don't see them always. I mean, you really need an ensemble and you need a long time scale to see if these jumps are happening. But for the thermal transport, that is really very important. Now, to analyze this now and being equipped with a measure of anharmonicity, we do this, what is called the CISO description. It's an artificial intelligence method developed when Runhai Ouyang was visiting Berlin. Runhai is now professor at Shanghai University. And the method, we call the method CISO, which stands for Sure Independent Screening and Sparsifying Operator. So just in simple words, what is CISO? CISO tries to find an analytic equation, but and again, the analytic equation should only describe the correlation. So we try to find an analytic equation, and we do this in the way that we start in creating a lot of analytic equation. So it's a combination of symbolic regression. So symbolic regression means, in fact, you are looking for analytic equations. And so we start with creating many billions of different equations, or in fact even trillions of different equations. And these equations depend on parameters which describe the material. And these parameters, again, could be the genes. But again, we offer many parameters, even the ones which may be turning out to be irrelevant, but we offer more than is really necessary because we just admit that we don't know actually what the intricacy and all the mechanisms are. Everything which is relevant, we try to offer. We build with all these parameters equations, and then compressed sensing is the mathematical method which from trillions of systems can define or identify the equation which has the best correlation with the measured or calculated data. And that brings us, this method brings us to the following description. This is just experimental data here. Experimental data, so you see the, sorry, I'm too fast on that. So here you see the CISO prediction on the y-axis. Okay, on the y-axis is a CISO prediction, and here is the measurement, and this is the quality of the CISO result. And these are all experimental data for very different type of structures. What I said in the beginning, what I really think is important to keep in mind, that all machine learning methods, also CISO, are a statistical method. They give probabilities, and therefore you always need, and we are really emphasizing this and showing this in these so-called violin plots. I'm not sure where my pointer is now. Okay, in these violin plots. So this is the prediction error for different models. So this is the model CISO which I show you, but I compare this really also with an old, 40 years old analytic equation based on physics. I compare it to Gaussian process regression, machine learning, and to kernel-rich regression. And what you usually people quote is the average number, and you see here the error of the average, the mean average error is the dot. Somewhat higher for Slack model, but then very much the same for CISO, kernel-rich, and Gaussian. But what is different is the shape of the violin. So the violin means if it's big or if it's broad, the width of the violin tells actually how many materials have this error. And if it's narrow, actually very few materials have the error. But you also see that there are bigger errors. So even if you have a certain situation, there could be an error which can be as big as here 0.6, or in the Gaussian, as big as even above 1. This you have to keep in mind, that you have a number which looks maybe good, but there's a risk that there could be actually a number which is, it could be as wrong as 0.6 or even 1. And so in that sense, you see that CISO is somewhat doing better than the other ones, but you always need this type of analysis, I think. Anyhow, so with CISO, as I said, you get an analytic equation, and the analytic equation which we get, I should say, actually we do this for the logarithm of kappa, and the reason is that the logarithm of kappa is only changing between roughly 1 and 4, so in a reasonable scale. Otherwise, it would be between 0 and 10,000. So just really to have the numbers on a more reasonable scale, we fit and describe the logarithm. And the equation which we finally get is a constant, another constant plus descriptor d1, which is one function, plus another constant descriptor d2 with another function. And these functions d1 and d2 you see here. These functions, as I said before, depend on physical parameters describing the material. We offer many functions. We offer many parameters. At the end, these functions here, which are selected by CISO, by this compressed sensing, only depend on 7 different parameters. And now you can again plot this map of materials. And this is this orange-yellow plot here. So we plot this as a function of descriptor d1 and descriptor d2. The points which you see here are all experimental data points. These are the experimental data points which you used for the CISO. And you see in the color code, carbon in the diamond structure is, I think, probably the best thermal conductor which we know. But we want thermal insulators. We want something in this area here on top. But the descriptors tell us where we should look. So you don't, once you have this map, you don't need to do a measurement for many things, because if D1 and D2 give you a material which is somewhere here, you could say immediately this is not a thermal insulator. You only calculate D1 and D2, and if you are here, then you would do a good calculation or a good measurements. So again, so you have this cloud, and you could say actually maybe you see the cloud if you just connect the outerlying data points. Maybe not every point here is really reachable, right? I mean, there's most likely nothing better than carbon in the diamond structure, but you could see actually there is really a type of a cloud connecting the outer points, and we are really looking for more points in this area here. Now, these are 7 parameters describing the material. Again, these parameters we would call the genes, right? And the function would be the rule. But you could also say, are really all the 7 parameters of equal importance? And for that, we did a sensitivity analysis, and looking really if you change parameters, does it really change the result very much? And then we see that only 3 of these parameters are really important. And that makes the analysis and the decision, what should you measure, actually much more easier. And these 3 parameters are the molar volume. So if you have, say, gallium oxide, gallium-203, it would be the volume of gallium-203, not necessarily the unit cell, but really the chemical equation. So the molar volume is important. You want a small Debye temperature. These are, I would say, classical quantities, and you want a large sigma A. And that means, again, what we said before, a large anharmonicity. And so you can now be very efficient, right? So when one tests a material and not really doing any analysis or not any detailed analysis, we just ask, is the molar volume bigger than 35 or 36 angstrom cube? Then we don't have to consider this material anymore. And you go to the next material. And only the materials which really obey this condition, you also look at the Debye temperature. Again, most materials are really falling out here already. And then only if both these criteria are fulfilled, you go to evaluate also the anharmonicity parameter. And so in this sense, you really can make very fast decisions without really a complicated or measurement or theory. And we did this so far in using 32 known materials, known because the materials project has calculated them, but they have calculated the structure. They have not calculated really the thermal conductivity. And we find immediately that 16 of these 732 materials exhibit a really ultra low thermal conductivity with a very small kappa value. And for these, we can then do and did a green kubo, expensive calculations, and supported, in fact, that they are really lying in this upper part of our materials map. So with this, I like to really come to my conclusion. So we are seeing a paradigm shift by data-centric science. The important point is this is really a different way of thinking. We don't have analytic equations which are laws because we are describing correlations. We have only predictions with a certain probability. If we do subgroup discovery or CISO, we end up with genes, which parameters, which in fact may have a physical meaning. So we don't know really the explicit relationship between these parameters, say the molar volume and so on, but we get an idea. In fact, you could interpret a little bit why this is. But these genes which enter could be genes which help the quantity which you want to have, but they can also hinder it. So you're also not completely sure, because life is very intricate and complex. So you have both aspects. Things facilitate something make something more difficult, and that's why one analytic equation for the as a law is not possible, but the correlation in terms of a rule is in fact what we do. And as I said, one should, in my view, look at creating maps of materials to find really in this infinite space the regions where you should zoom in to get smart knowledge extraction from complex data set, but not forgetting that this is a statistical method and not forgetting that you should do something like these violin plots, which we always try to do. And I showed that with two examples, namely catalysis and finding better thermal insulators. We have done several more data, but I just wanted to, examples, but I wanted to show you two different examples and in fact also the two different methods. The work I mentioned has been done mostly by Lucas Foppa and Tom Purcell, but of course several others in the group as well. And with this, I thank you very much for your attention.
Yeah, Neil, please.
So in terms of the when we talk about like those kind of machine learning or AI method, there should be a clear boundary. Like we are, as you mentioned as earlier, like we may sampling a very small area of this kind of vast base space. So in both of those cases you mentioned as two examples, seems to me that like the sampling space is not that large, and in comment like basically when you present those kind of a seesaw or any of the discovered genes, how do we basically specify some like of the viable, I mean, ranges, whether this kind of equation can be applied, whether at which condition they're not that doesn't work that well. Any comment on that? Uh-huh.
So I think what we are doing, This doesn't work? Okay. Because I have something here. I thought, does this work or not? I can use that.
Yeah,
Yes, better?
this one is better. Yeah.
I felt I understood him better before the loudspeakers were there because of okay. Anyway, so what you're doing here is, and I think you have said that, that you have this infinite space, and you know actually you should not really look everywhere, just look in this area. So you zoom in a certain area. Now, there is a risk with this because this zooming in this area comes from the information which you had. You have a subgroup, which of course is a subgroup of a certain mechanism which is acting in the data which you started with. So if there would be some other mechanism which was not in your data, you could actually have another area in material space. That unfortunately you would not really find. And so you're staying really with the mechanisms of the data. You can say you are biased with the information that you put in. But this is, of course, always in science the case. But you have to be, you need to know this, right? So my example is always if you would do this type of work with classical superconductors, you would not find the high TC superconductors because they are in a different part of space. So you will only really learn in what you have put in.
Okay.
You can, in fact, improve that. So you could actually, once you have the map which I've shown you, you could say, there are regions where I don't have data points. You could say, maybe I should look there, right? I don't need, so in this case, let me just actually go back to this. Here. So you could also say that it doesn't make sense to add more data here because I have a lot of information. But it could well be that something exciting is happening here. And that could be a different mechanism. So you should also use this map in saying, don't really repeat what is known already. Go to regions which are really maybe giving you some completely new insight.
Okay.
Is this roughly what you asked?
Yeah. That's basically answer my question. Okay. So another question I have is, basically, can you envision maybe in the near future how this field would go, which direction? As you can see, you have CSO, but there are also neural network way to discover things, and people are creating new databases. There are also autonomous experimental labs emerge as of today. So what's your take on, well, maybe next 10 years, next 20 years, what's going to be a big thing, like what will happen, basically? Can you just make justification of predict? Thanks.
So I don't dare to say actually how the field develops, but I can tell you actually what my plans are or what we are doing at the moment. I think all the different methods which have been developed in machine learning areas are really very important. Neural network is one which we started something like even 20 years ago, is particularly important. But you also see that neural networks have really advanced. I mean, you put some physics in the so-called equivariant neural networks or message passing. There are several things which you need to improve to really also get to a reliable neural network description. To some extent, I would say the problem, in quotes, of neural networks is that they are so general that when you're outside your range of learning or training, they're probably not reliable anymore because actually they're really very good in this as an interpolation, but not really so good in extrapolation. And that's why somewhat if you have these genes which also carry some physical meaning, they are good. Still, we are doing nowadays, actually also in my group, a lot of neural network, in particular really for creating forces and doing the molecular dynamics on a longer time scale. You have seen that that atoms are vibrating or they are moving, but then they are jumping. But this jump happens after 10, 20, 50 picoseconds. And you want to have this a little bit more reliable, so you combine ab initio methods with neural networks nowadays. But then there are other things. What at Tsinghua University, Yong Chu is doing is learning really the Hamiltonian, so that you also have a more efficient way to calculate band structures. So I think to make things more efficient and to go to bigger scales, what we cannot do ab initio, you do an ab initio trained learning type of approach. And there I see a lot of potential in the near future.
Are there any further questions? Yeah, you please.
Hi, Dr. Scheffler. So you've showed us how good the machine learning can find correlations, but what if the underlying physics have, for example, more than one mechanism? Does that confuse the algorithm?
Actually, this is exactly what I want to say, that this is what machine learning can do. So the world is so complex, so intricate, that means so many things are really going together or fighting against each other, that a simple combination of some laws will not really work. So that's why really you say, I give up the wish to describe things in terms of laws. I say it's correlation, and I keep it open what the mechanism is. So I cannot tell you really the mechanism. I can tell you, yes, it makes sense that the volume should be big, because then the vibrations are bigger. But I cannot explicitly prove that this is really the reason. Right? So the nice thing here is that you can do things which you could not really describe explicitly. So different mechanisms are included, but of course only the mechanisms which are in the data set which you give.
So you're saying that in this case, machine learning actually excels when there are several underlying mechanisms that couples, and it's hard.
I mean, to me, this is the reason why I do machine learning. I mean, I've done for 20 years catalysis and really calculating how atoms go to the surface, how they move, how they react. And I've seen this is surface science, but it's not catalysis. Under the high pressure conditions, things are so different. And now we are saying this is so complex, I bridge. So I start really from the basic genes, from the basic properties. I jump over the complexity and go directly to the property. And I still then can try to analyze what was the reason for the property, but I don't do an explicit description anymore.
Okay, thank you. One more question. I've noticed the examples you gave, they all have 2 or 3 descriptors, especially in this CISL one. You deliberately you originally have 3 or more parameters that you introduce to have dimensionless parameters, only 2.
Mm-hmm.
And in that way, you actually introduce something that has physical meanings. Like you have some part of causation that's introduced. So is it deliberate that you have just 2 descriptors?
Good question. So the first thing is the parameters, in fact, we call this, in fact, also parameterized CISO. So we multiply all the physical quantities by another parameter, which is also optimized at the end, and we add something. I think you, if I go back, where do I have this thing? Oh, that's a good question, which has actually several. So you see here the average mass, and we add a constant. So this constant is also part of the CISO analysis. This is just, and the other things are multiplied also, so that at the end, you don't make something stupid with units, right? You can only combine units which make sense. But with a parameterized CISO, you could have a unit like, basically as in physics, you could multiply something with h bar before you do something else. So with this parameterized CISO, you can in fact combine also systems or quantities which have a different unit. Now, why do I have actually only X and Y? There are two reasons. One reason is because it's a talk, and I can only plot two-dimensional. But the other reason, which is more scientifically, we in fact go to higher dimensions. So we use the dimension as a machine learning hyperparameter. Because also in CISO, you come to a point where you have something like overfitting. So you get actually, you do the analysis by learning on 90% of the data, and then you make a prediction on 10% which you have not used, and you look if the prediction error is really optimum. And you see the function of description of the dimension that first the description goes down, and at some point it really flattens or goes even up. That is the overfitting. So you basically identify the point, what is the best dimension? And very often we found 2 or 3 dimension. I think there's one case where I get 5, but with the complexity which we have in the functions, it seemed that it's not so high dimensional, but it can be 3, 4, 5 dimensional. But plotting is easier in 2.
Well, that's a question from me. So what's the typical order of a scale of the input data? I saw that this is like 100 something, like typical number of input data scale.
That's another good question. Because you start with physical meaningful parameters, I mean, in machine learning, in principle, if you do neural network, you need several thousand, if not 10,000 input data to train a neural network. CISO, because you start with physical meaning parameters, if your input is really good, you actually can already work with 10. So we have actually a very detailed analysis, another catalysis example, where people have done enormous work, which no one else would do for measuring 10 catalysts, but measuring that at a synchrotron, measuring it here, measuring it there, having really enormous number of data about 10 catalysts. And that was even good to also get a feeling what is going on and telling people now you should look no longer here because there you have enough data, look there to get something better. So you can live with small numbers, but again, I mean, you see the violin plot, you see in fact where you have data, and that guides you to get more. But with 10 data points, you can already get actually significant insight.
Thank you. Thank you very much.
Yeah, thanks for the nice talk, very inspiring. My question is actually very related to his last question, because I'm not an expert in this field. So I wonder, for example, this example you showed, the low thermal conductivity systems. My understanding is thermal conductivity is not a trivial thing to get, right? It takes a lot of effort to measure them and calculate them. So my question was also about if we have a very limited data set at the first place. You kind of said the algorithm can overcome the barrier. Is that correct? So even with how, yeah.
So what you see here are the experimental data which we trust, I should say.
Yeah.
So you say correctly, there are not so many experimental data.
Yes.
In fact, we found experimental data on something like 100 different systems. Compared to infinity, this is not very much. But actually from these 100 systems, we also felt some were not really so clean and some were even unstable materials. So from the 100, we selected only 75. So this is a 75, which people have measured. Again, because we have so few data, because it's really very elaborate to have a clean surface for doing this, or it's even more elaborate, I would say, or as comparably elaborate to do a full Kubo Greenwood, Green Kubo evaluation. And that's why once you have this, you now know where you should do the work, right? You now know that don't do it really in the range where you have enough data, do it really somewhere else to get another insight. So, but then of course, the work is still there. I mean, you can make the selection in a more educated way.
Yes.
But the work you still then have to do.
Right. Thank you.
So, even though this was not mentioned in the talk, but I thought it's still interesting to hear your opinion on the connection or difference of this more specific kind of machine learning approaches versus large language models, foundational models for materials. Yeah.
Not sure if I completely understand. So the connection to
Perhaps there is no connection, but I try to hear your opinion on, let's say, your vision on the possible future direction.
I mean, this was a little bit what I
right, but more specific on the foundational models for materials.
So at the moment, I would say I'm a little bit conservative in the sense that I see where I could use neural networks or other methods. But of course, there's something else which looks very promising, these large language models, right? Where I have to admit, it's actually interesting. So we have used that model actually even very early. So we had something. We had some idea. We had a so-called Kaggle competition. So Kaggle is somewhat a machine learning platform, and where you give data, and then you say the community should really answer a certain question. And we had created 3,000 data on group 3 oxides, and had said, actually, this is the cohesive energy, stability, and this is the band gap. And we asked the community the machine learning community, to really come up with a machine learning model. And when we gave a price of something like 5,000 euro or something, and within, so it was, I think, probably 2 months' time we gave the people. In 2 months' time, we had, I think, 900 solutions. And the best solution was, in fact, in the spirit of a large language model. It was really a guy from Japan who used n-grams to describe the solid, and then to describe via n-grams. So the methodology was not really a large language, but was the same mathematics behind it, using n-grams to describe really the solid and the behavior. So I think really combining things, and I had no idea. I mean, this was fantastic because I had no idea about this method before. So from this competition, we learned a lot about methods which are out there. So I think all these ideas will really enter our field. There's no question. And at the moment, you may know that some people are really starting also in China, like GPT, and really using this concept and the database which you have out there. You also know that the answers which you get depend really on the information which is there, and if there's only 75 data points on this, you may not get very reliable answers. In the past, at least, ChatGPT gave you always an answer, and in most cases I tried it, the answer was wrong. And then you ask ChatGPT, are you sure? And then she or he says, I'm sorry, actually it's different, and then gives another answer, which is even worse, but really very confident. So I think these machine things, these are very interesting. Whenever I could compare it, it was wrong, but when I not compared, then I'm not sure. I think this is one direction I'm sure it will go. This thing will improve, and we will go in this way. But at the moment in our field, we don't have enough data. One has to say that, right? Okay. ChatGPT was learning in all the text they could find in the world, right? And if you say, actually, I'm using just input from scientific data, there are not so many materials out there. But I think the field will move in this direction. It's very exciting, I think.
Okay, thanks a lot.
Yeah, maybe you go first.
Professor, thank you for your great lecture. And it seems that the subgroup model can provide us a lot of information about specific area. I wonder, is it possible to describe the boundaries between these subgroups? The boundary, I mean the areas between different subgroups.
Yeah. In principle, we would like to go this way, but we are not there yet. I mean, when you have this subgroup, you have these areas, but at the moment you also don't really, I mean, and you have these uncertainties, but you don't know really for sure where the uncertainty, you know that in principle there's an uncertainty, but you don't know where the uncertainty goes too big. And yes, I mean, if you would see that there are boundaries, but in fact, I would say in most cases, there are not boundaries. In most cases, these clouds will overlap, right? I mean, a system which is a good thermal insulator can also be a good photovoltaic cell. I mean, we don't know that really. There could be really exceptions. So I think there will be some overlapping. And in some cases, you want the overlap, right? You want an overlap with stable materials and a good thermal insulator. So sometimes you want an overlap, but I think the boundaries, I would, that's why I actually had chosen clouds, because I wanted to say that I have no idea about boundaries. But yeah, I think one should really look into this, but we have not done that.
Okay, and in the first work about the catalyst, the features are obtained from the composition. But in the second, I think the features also contain the structure information, because the Debye temperature or the force are calculated from the atomic information. My question is, how can we decide what kind of systems we only need the composition features, and in what kind of problem we need to add the structure the features?
No, I would say you should offer as many as possible, and then the mathematics will tell you that this is important and this is not so important. If you have enough information, you would do the learning for different structures and maybe actually really putting in structure information. But if you don't have this information, you cannot put this in, right? So it really depends on, but say, for example, if you would not have the relevant parameters in your feature space, which you're using for make subgroup discovery or for making system, if a parameter which is important is missing, you will not get a good description. But that's also the nice thing. You will see that you get a good description only if you have all the parameters which could be relevant with respect to the physical mechanism. But beforehand, you don't know that because of the intricacy. And I think you should always use all the information which you can get.
Okay, thank you.
Thank you. So I wanted to elaborate on this exciting statement of correlation does not imply a physical law, because you seem to be very confident about that. So just for an example, and you had this brilliant introduction about Kepler, and in the sense, how I see it, or one would speculate, is a correlation will be trying to derive Kepler's anomaly. So this would be, right, it is an empirical observation, and this could come out of the model. And in order to jump to gravitation, to Newton, you would need probably to put parameters that a little bit challenge the imagination of the model, right? You will have to put the mass and ask the model to look for radii, right? Which might not be relevant at the beginning, but I would not completely exclude it. So my question is, first, your opinion, obviously, and second, if you try to benchmark universal laws by putting things. So have you tried these benchmarks, these very simple benchmarks, to see if you take out a law?
Yeah, good point. I should have said that actually. If there is a law, you would find the law. So if there is a law, and if it's really just really one law, then you would find it. Most likely. The problem in the Kepler or Tycho Brahe Kepler issue was, and that's why actually Tycho Brahe was not successful, because Tycho Brahe was confident that the Earth is the center of life, and all the planets, and everything was really related to the planet Earth. Learning with these data, you don't see much of a correlation. But if you do a coordinate transform to the sun, then you see immediately these ellipsoids, right? So I think actually learning the law sometimes also actually, I think still requires some of your thinking. Going to the right coordinate system, then you see really that these data points connect very easily. But yes, if there is a law, and I think this has been done with, I think, second Kepler's law, and this has been done with Newton's laws, and if there is a law, then you would find them. So it's included, but in general, of course, if things are more complicated, if there are several laws playing together, then you are more general here.
Yeah. Thanks. I see no further question. Let's thank Professor Scheffler again, and the lecture is closed. We will go to lunch and to the fourth floor of our dinner, please. And you're welcome to join. If you want to come, just